Not just what it says, but what happens inside, as it plans, hallucinates, or even fabricates logic. In this video, we're breaking down how this AI microscope works, the real experiments behind it, and what researchers found. And if you stay till the end, you'll see how this changes everything from multilingual reasoning to catching AI in the act of lying. Let's get into it, the problem no one could solve until now. Large language models like Claude, ChatGPT, and Gemini don't follow hard-coded instructions. Instead, they're trained to predict the next word in a sentence based on patterns found in enormous data sets. This training process involves billions or even trillions of mathematical operations, but once training is done, the strategies these models use are hidden inside complex networks of weights and activations. Even the developers building these systems haven't fully understood what's happening under the hood. As a result, models can behave unpredictably. They might generate convincing explanations that aren't grounded in reasoning, or provide answers that look thoughtful but are just echoes of biased or faulty data. The field of AI interpretability has tried to address this with limited success until now. Anthropic's latest work introduces what they describe as an AI microscope. This tool allows researchers to trace individual computational pathways, identify patterns, and observe how Claude transforms input into output. It's inspired by methods used in neuroscience to study the brain, like how researchers identify circuits responsible for specific behaviors. Here, those circuits aren't made of neurons, but of patterns in the model's activations. This is the closest we've come to seeing inside the mind of a machine. In their March 2025 update, Anthropic applied these interpretability tools to Claude 3. 5. Haiku, an advanced language model optimized for high-speed reasoning. They focused on 10 core behaviors, including planning, translation, hallucination, and mathematical reasoning. The results revealed both expected and entirely unexpected patterns. Claude has a universal language of thought. Claude supports dozens of languages from English and Mandarin to Tagalog and French. But one of the first questions researchers tackled was, when Claude is reasoning, what language is it using internally to test this? Anthropic ran a series of multilingual prompts asking for the opposite of words like small in different languages. What they found was striking. Claude didn't process the word petite, French, xiao, Chinese, or small English as isolated units. Instead, the same shared features for smallness activated regardless of the language used. The model then activated a generalized concept for opposite, followed by the abstract concept of largeness, which was finally translated back into the language of the question. This pattern was not limited to just one or two test cases. It appeared consistently and with greater strength in larger models, Claude 3. 5. Haiku, for example, showed twice as much feature sharing between languages compared to earlier smaller models. This suggests that Claude reasons in a kind of language-independent conceptual space, a language of thought that forms the basis for all multilingual processing. This means Claude doesn't just translate. It generalizes. If it learns a rule or concept in one language, it can apply it across many others. This could explain why large models often outperform humans in translation tasks between languages they weren't explicitly trained on. And it also introduces a key takeaway. For developers, scaling up a model may not just increase accuracy. It may fundamentally change how it processes information that plans ahead like a human. One of the long-standing assumptions about language models is that they generate text one word at a time without any long-term planning. But Anthropic's poetry case study flips that assumption completely. They tested Claude's ability to write a two-line rhyming poem. For example, he saw a carrot and had to grab it. His hunger was like a starving rabbit. At first glance, it looks like Claude is just improvising, but when researchers traced the internal states of the model, they discovered something very different. Before Claude even started writing the second line, it had already activated concepts related to rabbit habit and other words that rhyme with grab it. It was preloading rhyme targets and then writing toward them, satisfying both grammatical coherence and rhyme constraints simultaneously. Anthropic went further. They used a method similar to neuroscience interventions, removing or injecting specific concepts when they suppressed rabbit. Claude defaulted to habit when they injected green. Claude rewrote the line to end in green even though it no longer rhymed. What this reveals is that Claude doesn't just guess the next word, it sometimes plans several words ahead, and it does this without being explicitly trained to plan. The planning behavior emerged naturally during training. This is important, especially when applying language models to domains like code generation, legal reasoning, or strategy-based games, where foresight can directly impact outcomes. Hidden mental math. Hidden mental math. You never see Claude wasn't trained as a calculator. It didn't study math the way humans do. It was simply optimized to predict the next word in a sequence of text, and yet it can solve problems like 36 plus 59 and get the answer right. But what's interesting isn't that Claude can do basic arithmetic, it's how it does it inside Claude's neural network. Researchers found that the model uses multiple parallel pathways when solving math problems. One pathway makes a rough estimate of the sum, another precisely determines the final digit. These two streams of reasoning then combine to generate the correct response 95. But when you ask CLO how it arrived at that answer, it doesn't mention estimation or digit-level circuits. Instead, it responds like a person might saying something like, I added 6 and 9 to get 15 carried the 1. As if it were following a school-taught algorithm. That explanation sounds familiar, but it's not true. Claude's actual method is different and more complex. This disconnect between internal process and outward explanation matters especially in high-stakes scenarios where users rely on AI outputs as fact. It shows that even when the answer is right, the reasoning might be entirely fabricated to sound plausible when motivated. Reasoning. Claude just makes things up. Not every answer that sounds logical is the result of real reasoning. Sometimes Claude simply makes things up. Researchers tested this by giving Claude a challenging math problem, but with an incorrect hint, an answer that sounds close to correct, but isn't. Instead of recognizing the inconsistency, Claude built an entire chain of reasoning to support the wrong answer. This behavior is known as motivated reasoning internally. The model skips the actual steps and instead works backward from the incorrect conclusion. It then generates logical-sounding explanations that match the target from the outside. It looks like Claude thought through the problem carefully. But under the microscope, researchers saw no evidence of real calculation, just a reverse-engineered justification. Philosopher Harry Frankfurt called this kind of behavior bullshitting, communicating confidently without regard for truth. Claude in these moments isn't trying to deceive. It's following its training to sound coherent, helpful, and aligned with the user's cues. The risk is clear. If users rely on long chains of thought to evaluate trustworthiness, they may not realize that those steps were fabricated on the fly. This makes it harder to distinguish genuine reasoning from persuasive noise, especially when the output is wrong but sounds right. The anatomy of a hallucination. One of the most well-known issues with large language models is hallucination. When the model confidently generates information that isn't true. What Anthropic found is that hallucinations aren't random. They follow a detectable pattern, and they often start with a failure in the model's internal control systems. By default, Claude is reluctant to answer questions it doesn't have enough information about. That hesitation is driven by a specific refusal circuit that activates when the model lacks confidence, but that circuit can be overridden if Claude recognizes a name or a familiar structure. Even without understanding it fully, it may activate a known entity feature. This can inhibit the refusal mechanism and push the model to answer anyway. That's when hallucinations happen. For example, when asked about Michael Batkin, a made-up person, the name alone triggered Claude's confidence. The model assumed it should respond, even though it had no facts to work with. The result, a completely fictional story that sounded real. Researchers were able to manipulate these internal circuits, deliberately turning hallucinations on and off by controlling which features were active. This demonstrates how hallucinations often stem from conflicts between the model's default caution and its tendency to generate complete, helpful-sounding answers. Jailbreaks coherence, and when AI gets tricked, despite built-in safety mechanisms, language models can still be manipulated. One tactic is called a jailbreak. A clever prompt designed to bypass restrictions, and in one case, study researchers watched it happen from the inside. The jailbreak used a hidden code: babies outlive mustard block. The first letters of each word spelled bomb. Claude interpreted the sentence as a signal and began generating instructions for bomb making. What allowed this to happen wasn't a failure of Claude's safety training. It was a conflict between safety and coherence. Once the model began the sentence, internal features designed to ensure grammatical flow and logical structure kicked in. These features pushed Claude to finish the sentence coherently, even if the content violated safety norms. Only after the sentence concluded did the safety mechanisms re-engage, prompting Claude to issue a refusal. This illustrates how competing goals inside the model, fluency versus alignment, can create vulnerabilities. The desire to be coherent can momentarily override the instruction to be safe. In adversarial prompts can exploit that. It also shows why monitoring output alone isn't enough. The dangerous response wasn't obvious until the sentence was nearly complete, but with interpretability tools, researchers saw the problem building up well before that point. Why this breakthrough matters more than you think. Conclusion: these findings go beyond technical curiosity. They're a step towards something long needed in AI transparency. With interpretability tools like the ones Anthropic introduced, developers can now observe what's really happening inside a model, not just the output, but the process behind it. They can tell when the model is planning, when it's reasoning across languages, when it's hallucinating, and when it's fabricating logic to please the user. This kind of visibility wasn't possible before. It's now becoming essential as AI systems get more powerful and are deployed in healthcare, finance, legal reasoning, and defense. Understanding their behavior becomes non-negotiable. We need to know why a model answered the way it did, not just whether it got the answer right. This work is still early. Tracing reasoning through a few dozen words can take hours, but it opens a path forward. Think of it like brain imaging for machines. Not every detail is clear yet, but we can finally start to map where thoughts form, how they connect, and where they sometimes go wrong. And for the first time, we're not just guessing what the AI is thinking, we're watching it happen. If you've made it this far, let us know what you think in the comment section below for more interesting topics. Make sure you watch the recommended video that you see on the screen right now. Thanks for watching.